this computer. And the first thing I guess I want to share with you is share is, I think I always start out this way, my Google Chrome, so that you can see the web page for Canvas. And just want to make sure we agree on what we're doing this week. Okay, we're continuing on in chapter 4, which is Schrodinger's equation in 3 dimensions, and that specifically we're looking at the hydrogen atom, which you should recognize because you, I'm sure, talked about it in PHY322 modern physics. I know my students did. I'm sure Campbell's students did as well. You have to admit, though, the depth is a little greater. Now, what we're agreeing to, I think, is, first of all, that is not going to be on the midterm, which I'll be posting on Wednesday. I can tell you I have my 3 questions pretty much picked out. I have to type them in, of course, and make sure that it's about the right length. They'll be due on Friday morning at the start of class. So by 11:30, you have to upload it on Friday. The scope, the last midterm went up in chapter 2 right up into scattering. So you should be expecting a scattering problem from chapter 2. And then chapter 3, the formalism, all the linear algebra stuff. Okay, and so all these tutorials. Now, I have some of you I gave your scattering worksheets back to, but I have them. Of course, you've seen the grade. My solutions are right here. If you want to see what you did, just send me an email either today or tomorrow. I went big with Amazon this weekend and bought one of those high-speed scanners, scans at about 40 pages a minute. And so if that's my plan for getting your work back to you now that I have that thing. So if you want the scattering worksheet or any of the homeworks that you turned in before break that you didn't get the paper copy back, a lot of people don't want to see those. I find at the end of the semester, I always have a stack that nobody really wanted or they left behind in the classroom or something like that. If you want to see your scattering worksheets, just let me know. I'll scan them on in and send them to you. But send me an email so I don't have to do it for everybody, because I know a lot of people don't want them. My solutions are right here, and so that should be helpful to you. Right now, there's 2 more tutorials that aren't posted. The solutions aren't posted for, and that is statistical interpretation, which I hope to have graded today. Oh, nope, I'm wrong. I graded that one last night. Generalized uncertainty, which I hope to have graded today. And then finally, using Dirac notation, which I should have graded tomorrow before you get the exam. Those are obviously important ones for the exam. On the homework, okay, homework solutions are posted up near the top, right? Lecture videos, syllabus, and schedule. Next thing down is homework solutions. Homework 6 was a scattering homework. Click on that right there, and you can see it was it was a barrier problem. Come on. This is what I don't like about Canvas, watching this little circle go around while it tries to load the document. Okay, it's clearly a scattering problem, so that's a good one to make sure you know how to do for the first exam, for the next midterm here this week. And once homework 7 is turned in by everybody, remember it's due Wednesday, I'll immediately post the solutions. I hope to have it graded sometime Thursday-ish. So since you may have it back, you may not, but you'll be able to see the solutions before you turn in the next midterm. So I'll have my solutions posted right back here below homework 6 solutions. You'll find homework 7's. Come on, don't jump around on me. You'll find your homework 7 solutions as well. All right, so that's the stuff. That's as I said, open book is the rules of engagement, but you can't talk to another human being. Open book includes websites, anything you use to do mathematical calculations, anything like that is all fair game. You just can't talk to another person. All right, that'll be up on Wednesday. Stopping to share now on that, and we'll switch. There it is. Get those letters out of the lips there. We're sharing hopefully my PowerPoint here. And this first slide I want to start with, boy, it's an eye chart, but it is significant, I think, for what we've been doing in chapter 4 since we started. You kind of read it right to left and then down, and you start with Schrodinger's wave equation, right? And separation of variables is the overwhelmingly popular technique as we're going through this. The difference, of course, from chapter 2 is that Schrodinger's wave equation has a Laplacian instead of a second derivative with respect to x. And so we can do this problem in 3 dimensions. But separation of variables to get the position that's now the wave function that now is a function of position, r, x, y, and z, and a part that's a function of time. And so we separated variables. And when you separate variables on Schrodinger's wave equation between time and lowercase psi, you get the so-called Schrodinger's time independent wave equation, or eigenvalue equation, energy eigenvalue equation, because it is an operator on psi is equal to a constant, the energy eigenvalue, times a wave function, okay? So that's the deal. And then what do we do to that guy? In 3 dimensions, we separate it again, because we're working in spherical coordinates, r theta phi. We separate it into a radial piece and an angular piece, okay? Now let me get my pen here, because I'm going to want to start writing all over this. And once we separated, we got 2 equations. Admittedly, that's a wacky separation constant. You'd want a constant to be like C. Instead, we picked this L and L plus 1. And this equation here was the radial equation. You see it's only a function of r, and the function r that we were separating here, we held that in abeyance for a while, and we went on and we worked the angular equation right here. And you see these 2 separation constants are equal. They were both on the same side. They had to add to 0, so one's the negative of the other. Once again, separation of variables. We separated this y function into a theta and a phi piece. Just jam that back in here, separated. We got 2 differential equations here. One was one that, you know, Hamilton had to have gone through with you in your differential equations class. It is the classic second order differential equation, and its solution in this case, because it's a negative sign right here, is a complex exponential. When you bring it over to the other side of the equation, it comes as a positive m squared. And I've heard that referred to, I often refer to it as Helmholtz's equation, and that is the solution to Helmholtz's equation. You may notice some things that Hamilton would have taken points off as you submitted that as a solution in his class. There's no constant out there, and there's no m being negative, no minus im phi in that equation. And we're going to make m be negative. We've already agreed on that. The constant will just, when we get the solution to the next piece over here, the theta equation, we'll put the constant over there because we're going to have to remultiply them back together on this guy. Okay, so that takes care of the phi equation. The theta equation now is this differential equation. That differential equation is called Legender's differential equation, solved by Legendre. And there's his solution. It's his associated polynomial. Okay, and as promised, there's that constant. So that's why I don't have a constant right here in the phi equation, right? And the guy who came up with a nice way to, with a mathematical function, define what Legendre polynomials are, actually Legendre associated functions and Legendre polynomial. This guy right here isn't necessarily a polynomial because of that square root right there. This guy absolutely is a polynomial. And you can see this guy goes right here, and then you have the solution to the differential equation right there. Rodriguez was the guy who put these together. Okay, and we played with those for a little bit. Most of you submitted the worksheet tutorial last Friday on that. And the last thing we said was, now you take this and you take this and you stitch them together to get y, which we call the spherical harmonics, y. Okay, and it is just, as promised, the sum of this guy, the associated Legendre function, and this guy right here. Okay, and that this thing in front you should recognize as a normalization constant. I don't know, that'd be a great final exam problem, wouldn't it? Show that that is a normalization constant. Kidding. I never did that in graduate school either. We'll just accept that it is normalized. We can check that it's normalized, but to solve for it would be a tedious bit of mathematics. But anyway, spherical harmonics, right? That's the function. That's half of our overall solution. Where's our half of it right there? Okay, half of our overall solution for phi, for the wave function psi, I should say. And if you ever want capital psi, we just say we always, as we did before, just multiply by e to the minus I times whatever the energy eigenvalue is divided by h bar. Okay, held in abeyance was the radial solution. Boy, that guy was fun. We spent a little bit more time on it, I think, or at least it feels like it. We're finishing that up today. That's where we're going. Okay. And so the first thing we did to this equation was redefine variables. R times little r is going to be u. And so it's a way to substitute this guy. And so I showed the derivatives, and it's a pain. And then the other substitution we're going to make is, instead of being the variable r, we're going to replace that with the variable kappa times r, okay, is this rho. And by rho, I guess, well, you mean that. What do I mean by kappa? Kappa is the same meaning it had in most of the scattering problems we looked at. Not a complex number, because we expect this to be a bound state for hydrogen. And so E is a negative number, which will cancel that. So that's just what kappa is. Okay. There is a rho zero, which is a bunch of constants that come from this thing. When you make all these substitutions, the neat piece is it becomes a simpler looking differential equation. But not so fast in solving it. Just when you think you've substituted once and you were done, no, we're going to try to get U split up into three pieces. We showed these two guys were asymptotic. You might see that when you see the form of this guy, you'll go, did I really need to strip off that guy? And all it does is it makes the series solution look nicer. It actually starts with a term that's non-zero. If I didn't strip that off, you'd start with a bunch of zero terms before you got for our solution for this thing. I call it V. It may be a nu. I never can tell from that what we're trying to show. But we stripped off the two asymptotic solutions. And this guy, boy, that contains all the information on the radial solution to Schrodinger's wave equation. Okay, we did a power series solution. We worked through it in the same manner you often do. I've heard that manner referred to as method of Frobenius. Different people call it different things, but that's what my math teachers always called it. One of the things the method of Frobenius always yields for you is something called a recursion relationship. Here it is right here. In the quantum mechanical world, we realize that guy right here, okay, is that coefficient in this solution, which is part of U. And U, of course, is part of R, and R is way up here, part of the overall wave function. The wave function has to be normalizable. So that means this can't be an infinite series of terms. It has to truncate, is what we say. There has to be an end to that series. While I said infinite here, there has to be a point where these coefficients go to zero. That's critical. Okay, because if they don't go to zero, if there isn't some C sub j that becomes zero, and then all subsequent C sub j plus 1, plus 2, plus 3 also go to zero, the wave, this series will never converge. You'll never be able to get a normalizable R, and so your wave function won't be normalizable, and then it lies outside the Hilbert space, which we talked about in chapter 3, and so it's not an allowed solution to Schrodinger's wave equation. Well, how do we make this happen? The recursion relationship always starts with like maybe C0, and it allows you to figure out what C1 is. And then once you got C1, you jam it in here, and that allows you to figure out what C2 is. And then C2 allows you to figure out what C3 is. And we've decided that there's some value of j plus 1 that we want to be equal to 0. And then we want all others above that to be 0. The only way that can happen is if the numerator here goes to 0. Okay, now I did make a substitution on this numerator from the original power series solution, because you had a minus rho naught right there. We've defined n to, well, actually it was rho naught outside the parentheses. We defined twice this number n to be equal to rho naught. Remember, rho naught's just this grouping of constants right here. But if I can make that numerator go to 0, the series will truncate. It won't go any further. Okay, just literally push symbols around the page here. You see kappa is a function of E, right? Rho then, now kappa is right here in rho naught with all these constants. It looks like between these two equations right here, I can find what the energy is as a function of all these constants here, right? And I think we also decided that kappa can be simplified to be written like 1 over this n times a, where a is the Bohr radius. And so the bottom line of all that is there is a way to get the energy eigenvalue out of this substitution step right here, and the fact that I defined rho naught to be equal to twice this number n. It turns out that energy is a function of this number n, and if you look at all these constants right here besides the 1 over n squared, they turn out to be minus 13.6 eV. And you should recognize that from modern physics. Those are the energy eigenvalues for the hydrogen atom. And that would allowed us to do things like figure out what the lines are from a hydrogen lamp, for example, that's glowing. We could figure out what frequencies are present from that. More on that in a minute. But the bottom line, though, I guess, is these are integers, okay? And there are specific values of energy eigenvalues. These are discrete eigenvalues, as opposed to the continuous type we talked about for free particles in chapters 2 and 3. Okay, so that's a mouthful, but that's about where we were. And I think we were looking at what we hoped would be that simplest, I guess, lowest is what I really want to say, eigenvalue of energy, where n would be the lowest number it can be, 1, okay? And so the energy of that particular electron then in that particular state, in that particular eigenstate, in that particular eigenfunction would be minus 13.6 eV. And so we're trying to figure out, well, what does that eigenstate, that eigenfunction look like, okay? And so I think if n is equal to 1, we got to do a little work to figure out, well, where does this series solution truncate? And the answer is, if n is equal to 1, n is equal to 1 right here. You can see I got 1, 1. I think that must mean if I want this guy to be 0 for C0 to exist, but I want C1 not to exist because I want this series to be as simple as it can be. Remember, that would be like C0 plus C1 rho plus C2 rho squared plus however many terms I've got. In the simplest of these, I would think you would expect only to have C0. And that means that the maximum value of J in this thing would be 0. N is equal to 1 to get the lowest energy. And so the only way to make this thing go to 0 is if that's 0, that's 1. Well, L has to be 0 as well then. And we'd showed previously in the quantum states for the angular solution that M can't be any bigger than L. It can be minus L plus 1, minus 1, 0, plus 1, and then L minus 1 up to L. And so if L is 0, well, M has to be 0 as well. And that does, of course, force C1 to be equal to 0, which is what we would expect for the lowest state. And so now we've decided two things, I guess. N is equal to 0, L is equal to 0. Three things. M is equal to 0. Those are the so-called quantum numbers for this lowest state, okay? These three facts right here. And so I guess we look at the spherical harmonics where that would be 0, 0. You can go back and look at the table for spherical harmonics. The value, the normalized value of it is just a constant, 1 over 4 pi. I want to make a quick aside on that table. If I think Jacob Stein, you noticed that there's a question on the 1, 1 state. Is there a negative sign or not is the question. And I think the best answer I got doing some research on that over the weekend is it depends what reference source you read. That minus 1 to the m power that's in the spherical harmonic equation, some people do different things with it, okay? And really what we're talking about is what's the P11. If you look in our textbook on page 137, where it's the table of the P's, the associated Legendre functions. For P11, it's called minus sine of theta. But then you go and look at Y11, he injects a negative sign, and it should cancel. I just should tell you that I went to a math book one I used in graduate school. Everybody should have a math book in their shelves. Unfortunately, at Washington College, we don't take a math methods course and an applied partial differential equations course typically. Arfken is a book that a lot of people use. There's a book by a lady named Mary Boas. It's a very good book, considered a standard. I went and I looked at the table of associated Legendre functions for that. I looked up, well, what's P11 plus sine of theta? If you read the footnote in our textbook, Griffith says he's adopting the convention of Mathematica of all things, which I think is a dopey thing to do. He didn't do that in his earlier editions. He was more in coherence and consistency with the math books that are out. But he did change, and he puts a footnote. He says why he changed, and that is to be consistent with what Mathematica does, which I guess becomes the new standard of consistency. Remember, a lot of these mathematical things are conventions, how you choose to define that. Because from a practical point of view, once you've got y, which gives you a piece of the wave function, the first thing you're ever going to do with it as a practical physicist is square it, right? Because you want psi star psi. You're going to multiply it by its complex conjugate. So if it's negative, you're going to multiply it by itself as a complex conjugate. And negative signs are going to cancel whether it's there or not. So this really is a convention that doesn't mean a lot, but it does. It's a question, and it's a good question. It just it's a convention that people don't agree on as of this moment in our physics history. Any event, back to our wave function. There's 0, 0, and I guess if this guy is just a constant, we put together r, knowing that n is 1 and l is 0 here. And remember, it's just u over r, rearranging this guy. And u is all of those things. So I went 1 over r, and I put all those things right in there. For the case of L equals 0, makes that to the first power. That guy's just there. And then we just decided that the only term in this series that's not 0 is the first one. And then C1 and C2 and all the others will go to 0. And so you just kind of string those all together right here. And that's what I did in this line right here. And so 1 over r, there's rho. Rho would just be r over a here, because remember, rho is r over na, kappa, 1 over na, we showed the other day. And so the constant C0, and then e to the minus r over a. And of course, how are you going to get C0? You're going to normalize this wave function, right? So we said the way you normalize the radial portion of the wave function, there's a division of constants in dv, or dr cubed, the volume element, and we said it's r squared sine of theta, there's an I missing there, sine of theta, dr d theta d phi. Now we said when we're normalizing r, we're going to use this piece and this piece. And when we're doing the angular normalization, we're going to use what I've called d omega, the solid angle, which is the rest of the pieces. So took my solution that I wound up with right here, okay? Saw those things just squared, bring them out front. There's the rest of my solution with the r squared dr. I used this template integral table integral to solve this integral right here, because it's of the form x to the n, where n is equal to 2, and it's divided by the alpha, so alpha would be a over 2. The negative sign's already there, so we're good to go. You just got to put n factorial, which would be 2 factorial, alpha to the n plus 1, which is a over 2 cubed. That's why I did this, start canceling stuff. Sure enough, solve for the constant 2 divided by square root of a is the value of the constant. And so I just put that right there, okay? And so that means the overall wave function then is this, which is r. And I said, pulling it off the table, that is the spherical harmonic y. So I just lumped it all together and simplified a little bit. And that's the wave function for the lowest minus 13.6 eV energy eigenvalue state of an electron in a hydrogen atom. Something you might have known from modern physics, but I think a whole lot more depth and detail in arriving at that answer. Anything I want to say about it? Yeah, I do want to point out, I'm going to show you some more of these R's in a bit. Notice that it has A, which, don't forget, is the Bohr radius, about half an angstrom, cubed square root in the denominator. The picture of a lot of the wave functions higher than 1, 0 are for R are written out and graphed, and they're always graphed as with a to the 3/2 power being multiplied by the wave function. So the guy who graphed them brought that guy, put it over there, and drew the curves. And so you'll see a factor of a to the 3/2. That's where it's coming from. All right, so that's, I think, is still a review from last time. Let's look at the n equals 2 case, just for grins, okay? And remember, R now will be 2, And the question, of course, will be what will L be? All right, and so this is the putting in 2 right here, 13.6 divided by 2 squared minus 3.4 EV. By the way, this number 3.4 EV or the 13.6 EV, you may have learned in chemistry or in your modern physics class, you may remember me saying it, that is referred to sometimes as the ionization energy as a positive number of EV of the same magnitude. Because if this electron currently is in the state such that its energy eigenvalue is minus 3.4 EV, if I want to get that electron out of that state, completely free of the hydrogen atom, I have to give that hydrogen atom at least 3.4 EV of energy. Okay, and then I can completely rip the electron out. If it's in the ground state, I have to give it 13.6 EV of energy. I can completely rip the electron out of that state. A chemist would tell you you've ionized it then. Okay, when you ionize hydrogen, you're left with just a bare proton, right? Because that's all that's in the nucleus. You do that to another atom that has more electrons, you just rip that last one off. You create an ion, okay, with it's an atom that's missing one electron, and you say you've ionized it by giving it exactly this amount of energy that that particular electron's bound state would be. Okay. Any event, that's just a bit of nomenclature and why. I want to continue on though with n equals 2. If n is equal to 2, I would kind of expect to increase the wave state that I would the eigenfunction that I would get maybe 2 terms, right? And the first 2 terms would be those 2, and so I would want the maximum value of j to be 1, okay, and I should also get 0. But I would want 2 in this recursion relationship right here. I don't know why I've got it written out again. I would want this guy to go to 0 when j plus 1 is 2, so j is equal to 1. So the maximum value of j I want is 1. All right, so let's see. This is now 2. This is now 1. And so what if I make this guy 1? Then I got 1 plus 1 plus 1 minus 2. So that would be 3. Let's see, is that going to work out for us? When that's 1, nope, that's not going to work. So if j is equal to 1, that must mean L is equal to 0, right? And then I've got 1 plus 1 minus 2. Yep, that one works. So if the maximum, if I have the first coefficient, I can have L equal to 0, in which case I have M equal to 0 as well. What about when j is equal to 0? Would that work? Well, then I'd have 0 plus something. It's not 0 yet. So I get 0 plus 1 minus 2. In that case, I could have L equals 1, right? I could have the j0, that guy. I would be allowed to have L equals 1, then 1 plus 1 minus 2, 0, and then I wouldn't get the next one up. Okay, so I could have L equals 1, and we saw from the angular case, the angular wave function solutions, that if L is equal to 1, then M could be minus 1, 0, and 1. And that was because of the derivatives you would take on the Legendre functions and polynomials. There was a limit. M couldn't be greater than L, remember? Okay, and so in that case, I guess C2 would go to 0, and that would be good. And you still could have the other case, L is equal to 0, and M is equal to 0. So it looks like there's 4 different states there, 1, 2, 3 associated with that one, and then that one as well. And in that case, the series solution here would just be the first term. This guy right here would have a series solution of both terms. Make sense? 4 states. All right, so I guess let's do, which order am I going to do this? Yeah, let's do, this is the C2 is equal to 0 case, and I guess this would also be the, yeah, okay, so I'm going to go only from j equals 0 to 1, because that's the maximum value, in which case I have both terms, but I can only have L equals 0 for that case. Okay, so when I put that 2 L equals 0 together, it goes 1 over R, and do I have that equation? Yep, okay, from up here in the corner, 1 over R. I can only have L equal to 0 for this case. Okay, L is equal to 0 because I'm right here. The only way to get that is L equal to 0. And so I have rho here raised to the first power, because L is equal to 0. I got, this case, how did I write it? I wrote it over there. Rho is R over 2A, A again being the Bohr radius. That's the exponent there. And then I brought those guys right there. I have to normalize in order to get that, but that's my wave function for the 2, 0. Okay, and 2, 0 is, I'm allowed to have both a C0 and a C1. Okay, let's see. Yeah, and that's why I guess I wrote this right here. All right, so what about the other case? What about R21? Okay, R21 would be 1 over R and be rho, but now I can have an L equal to 1. Okay, so that, this actually should be up there, I think. I don't know why I wrote it down there. In this case, L is equal to, it could be equal to 1. And so up here I have 1 plus 1. That's why I put 2 times rho. Still N is equal to 2. I still have e to the minus rho, R over 2, or radius. And I've only got the one term from V, the C0 term, only the first term. Okay, and again, that's the state for when N is equal to 1. I'm sorry, N is equal to 2 and L is equal to 1. And I have those two states right there. Now, unnormalized, I guess in order to figure out what the constant C0 is, you'd have to normalize them. I'm not going to do that, but I do want to point out that, well, what if there's a 3 now, I guess? What if N is equal to 3? I always like doing this. And so what are the possible values of L? Well, I think, like before, 0, 1, we've already said that for 2. In this case, if you went through the same thought process, now you get 1, 0, 1, and 2. The relationship is that this guy right here for L, it's always equal to the principal quantum number, N is what we've come to call that, less 1. Okay, and so M sub L, M is what we just call it. We might subscript it L later here. For this state, there can only be a 0. For this state, there can be minus 1, 0, and 1. Because remember, we said M can go from minus L to plus L in integer steps. Okay, and so that would be the number of states for that. And let's see, for this guy, when N is equal to 3, L is equal to 2, I can have minus 2, minus 1, 0, 1, and 2. Okay, and so for the N equals 3 case, I have, let's count them up here. 3, 0, 0, 1, 3, 1, and then there's 3 more states for that, total of 4. And then for this one, I have 3, 2, 5 states. So I got 1 plus 3 plus 5, looks like 9 different states here, right? For N equals 3, 9 states. Let's back up a little bit. N is equal to 1. We only had 1 state, right? L had to be equal to 0. M had to be equal to 0. 1 state. We looked at N equals 2. We had 2 possible values of L. L equals 0. L equals 1. And then let's see, M had to be equal to 0 for this case. And M could be either minus 1, 0, or 1 for this case. Let's count up states here. Obviously, for N equals 1, there was only 1 state, right? Only 1. But here we got 1, 2, 3, 4 states for N equals 2. Let's see, for N equals 3, 9 states. Anybody want to make a wild guess how many states I can construct if N is equal to 4 from this pattern? And of course, you can see the answer is N squared. And the reason is because each value of L has 2L plus 1 states. If it's 1, I get 3. 2 times 1 plus 1, 3. If it's 2, I get 5. 2 plus L plus 1. And I added 5 plus 3 plus 0. And that's what this side is doing. We call those number of states the degeneracy of the energy eigenvalue, eigenfunction associated with that eigenvalue energy, okay? And so what that means is, for example, in N equals 2, there could be a whole bunch of electrons, all that have energy, we said minus 3.4 eV, and yet there are 4 different mathematical functions that can define the wave function psi, each one of those with a different value of r. We call eigenfunctions, eigenstates, wave functions that all have the same energy eigenvalue. We call those degenerate eigenfunctions and eigenstates, okay? And we've just kind of gone through a little pattern to see what the degeneracy is for hydrogen atom based on what the quantum number, what the principal quantum number n is. It's n squared. All right, here's a picture of that, I guess. This is, by the way, what Griffiths calls this J max plus 1. The maximum value of J, like 0 or 1, as I said, plus 1 more. So he's plotting this. And I'm not sure what the value of introducing that is. This is the principal quantum number 1, 2, 3, okay? And you can see for n is equal to 2, there are a bunch more, there are different states I can have. This would be, I guess, L equals 0. And this is the L equals 1 state, okay? And you can see that this would, I don't know why the 0 went away right there. This would be L equals 0, L equals 1, L equals 2 for the n equals 3 state. And of course, in L equals 1, there's 3 values of m. And right here for L equals 1, there's 3 values of m. For L equals 2, there's 5 values of m. And you can see the degeneracy. They're different states. And oftentimes it's just a rotation that makes the states different, but they're unique mathematical functions. All right, the chemists have some notation they use for this degeneracy. The chemists use this, this notation where they talk about, say, a 2p state, for example. Well, 2 is the value of n, the principal quantum number, and then p is this pattern right here for the value of L, so they use S, P, D, F. Those were spectroscopic notations that they were seeing. So in the case P, that means L is equal to 1. So that's a possible one, right? 2, 1, that works. The other possibility for 2 would be 2s, right? Because you can have L equals 0 for a 2 state. So the first number is the quantum number, and then this letter, for some reason, is what tells you what the value of L is. Okay, and that's about it. Boundary conditions require that n has to be 1 greater than the maximum value of L. All right, there's always a mathematician around in this business, okay, to name an equation after themselves. And it shouldn't surprise you that this series solution for V, well, it has, which is this series solution right here, does have a guy. It was Laguerre, and there are associated Laguerre polynomials and Laguerre polynomials, which are the solution for these guys right here. You can see they're just constants, polynomials in X, okay? And polynomials in X, but you've got one more derivative being taken, another set of derivatives being taken. I will point out that this is our textbook's notation. The worksheet chooses to call this guy P, and then call this guy P minus Q. They're equivalent, but you should just recognize they'll be a little bit different in notation. And so if you're trying to get, though, I guess, and this is sort of an important point, if you're trying to get, because you're in a state where you need, okay, n minus L minus 1, you need a particular value down here. That means when you're finding this polynomial, okay, you want to go 1 higher, don't you? Because or 2 higher, depending on what the value up here is. But this is the guy Laguerre who figures out this is a way to state the same series solution that we've been working with so that you can tabulate it. And Laguerre is the guy who came up with the math function and tabulated it. Now, it is a weird indice, n minus L minus 1. 2L plus 1, and then of course X gets replaced by 2 rho. Remember, rho is R over N or radius. Yeah, so it is kind of an odd indexing, but it works, okay? And it kind of almost makes sense a little bit. N minus L minus 1 minus N plus L plus 1. It's the thing that it's exactly that piece right there. And then, 2L plus 1, that's the number of the degeneracy, right, for each of M for each value of L. So there is something to this, I guess, why that turns out to be why it's 2P. Well, that's just the way it's been defined. Okay, so this is a quick way, I guess, rather than working through these polynomials to figure it out, you just do it as a lookup. And that's what the worksheet for today, which is posted on Canvas, has you working through. Okay, once you got L, which is this V right here, okay, you come over here, you multiply it by e to the minus rho and rho to the L plus 1, and then you figure out what R is from that, and then you can put it all together, multiplying with the spherical harmonic piece to get the full wave function. If you need capital psi, of course, you got to multiply by e to the minus I E over h bar times t, what we've been calling the wiggle factor all semester. These radial wave functions, the Laguerre polynomials, have been tabulated. I think I promised you that there would be a kind of an odd thing when they're graphed. Okay, there'd be this a to the 3/2 right here. Okay, that's not working. What color am I using? Pen. And so it's here. This is exactly what I was talking about. Okay, these R's are tabulated, and somebody graphed them here. And I just, to remind you what rho is, R over NA. A is the Bohr radius. N is the principal quantum number because of that. And remember, the first one had the A square root of A, and so do all the rest. And so that's why they're plotted not as R's themselves, but as R's times the Bohr radius to the 3/2 power. And so then it's kind of like normalized to that scale. Okay, and you can see they're kind of hard to pick out. The one that we worked with and actually normalized and got all the values for was R10. And as expected, it's this dashed line right here, which is just this exponentially decaying function as a function of not R, but as R over A, interestingly enough, on the x-axis. So you can see how they're plotted. I guess the full hydrogen wave function then, putting all of this together, okay, is V gets you U, gets you R. The V's come from the Legendre polynomial, and it's a very similar thing we did with Laguerre polynomials. Very similar thing to what we did with Legendre polynomials, which is probably why sometimes we'll say the wrong dead French mathematician's name. The associated polynomial is always the thing with the two indices, like the associated Legendre functions here. The associated Laguerre polynomials have two indices. And then what you're always winding up doing is you're getting this guy, and that comes from another just mathematical polynomial, just like this came here. And so these mathematicians like these solutions that were polynomial series, and that gets you the Laguerre polynomial. You bring it up here, you take some derivatives on it, and that gets you the associated Laguerre polynomial, which is V. And then V goes into here to get U goes over here to get R, okay? And so, again, somebody took these things, and what we got right here is just that piece comes in right here. The V piece comes in right here. You can see we got this guy right here jammed in right there. And should that be N plus 1? That should be, I'm sorry, L plus 1 right there. That's a typo. That has to be L plus 1. Let me make sure that that's what the book says. The book's got a typo, and I just copied it wrong, but you can clearly see that's rho to the L plus 1. That's e to the rho, and that is our Laguerre polynomial. So let's see if I copied it wrong or if there's a typo in the book. And the answer is I'm going to go with it's a typo in the book. In any event, that guy there is a problem. But this right here, normalization constants again, right? So we normalized R, and those must be the normalization constants, just like those were all the normalization constants on Y. You put these all together, you multiply this guy by that guy, you got all the normalizations, and that will be your full wave function. So it's there to look at. All right, I tried in modern physics in my class to show you what some of these look like. And these are the associated Legendre functions, I guess, Y. And These were the Y's, okay? And I subscripted them this way as opposed to up down, which is what our book's notation is. I think in the book I used for modern physics, they were written next to each other as opposed to up down. But that's what the 0, 0 state looks like. And this is what then the P10 looks like. And you can kind of picture this guy right here, circular in symmetry, but it has a preferred radius. Okay, and our textbook has taken that, and I guess it hasn't drawn that one because it's just too simple. But then our textbook looks at, okay, what about n equals 2, which is this next row right here, and that's 0, 0. Okay, but you can have 1, 0 as well for the L and the M, and then L plus 1, 0, minus 1. Well, there's the 0 right there. Those were the two different states for the spherical harmonics. That's what they look like plotted in 3 dimensions. And then the two values of n that could exist, 2, 1 and 2, 0. One of them has 1 hump and the other has 2 humps. Okay, so you kind of think spherical symmetry for the, I guess, 2, 0, 0 would look like that, but then the 2, 0, 0 has 2 kind of maximums, 2 radiuses where there's a maximum probability of finding the electron, but with circular symmetry. On the other hand, these guys right here that have L equal to 1, they just have one place where there's a maximum probability of finding the electron. And so I just want to show you what those look like coming down this column right here. There's 2 radiuses where there's a maximum probability of finding it, but it has pretty much spherical symmetry, doesn't it? The 1, 0 is 2 kind of balls sitting right on top of each other, but there's only one maximum radius. And same thing with the 1, 1, only it's kind of the donut looking thing from the previous slide with one radius that's a maximum radius for finding the electron. You can go through the same game for the n equals 3, a whole lot more states then, and they're related to all of these spherical harmonic wave functions. And then of course, these various radial wave functions, you kind of blend them together in your mind's eye and you get a picture like those 2 columns right there for the 3 states. And you can play with those on your own because I think I'm running out of time here. This is a pay website that the author recommends. He says, hey, go to these guys right here, and you can see how they're these various states, 2, 0, 0, 3, 1, 1. He doesn't graph them all. You have to pay to get the website, and they'll print out these probability distribution functions in a plane for these various wave states. All right, one last thing, and we're done. And it's called the spectrum of hydrogen. And you may remember back with Rydberg in modern physics, you said, okay, so I got a hydrogen gas in a tube, and I put it with a high voltage and I make it glow. What colors do I see? And you know, if you believe this wave function stuff and these eigenvalues, each wave function, each state has its own energy. And the reason you were seeing glowing is what happens to these electrons is they can transition between the states by either absorbing energy, that drives you from a lower state to a higher state. An example of that is pumping a laser. And then once they're up in that higher state, they can relax down to a lower state. That's when they glow. They give off the energy. And the spontaneous emission in a the laser is one example of that. And you get electromagnetic radiation. Photons are given up. And so what's the energy of that photon? Well, it must be the difference between the energy of the 2 states. That's the energy. And we're going to give the symbol gamma for the photon. That's what we use. Okay, so the way you'd find the energy of that photon is you just take the difference between the initial and the final energy states. I factored out the minus 13.6. Remembering that the energy of a photon is Planck's constant times the frequency. Our textbook uses nu, definitely a Greek nu, not a V for the frequency. Other textbooks, it might have been F, same thing. We're talking about the speed of the electromagnetic radiation, the speed of light divided by the wavelength. Okay, and so we could substitute that in right here in hc over lambda must be equal to this. And then you can divide by c and divide by h and solve for 1 over the wavelength. And all these constants right here are the same constants that made up 13.6 before I substituted that number. Well, you can see that H here, but I got H bar there. I can make them all H bars by putting in another factor of 2 pi, and so it becomes H bar cubed. And this grouping of constants here stays the same, and hopefully you recognize that was something we call the Rydberg constant. I got rid of this negative sign by reversing the order of the two indices. I went initial minus final. When it was negative, it becomes final minus initial, it becomes a positive. This is that Rydberg constant we studied in modern physics. It has the value 1.097, 10 to the 7th inverse meters. If you plug mass of an electron, Coulomb's constant, charge on an electron, H bar from the right table, and 3 times 10 to the 8th meters per second for the speed of light, you will get Rydberg's constant, and it allows you to find the wavelength that would be released. And this is what I want to make sure we're clear on. As the electron falls from one state at a higher energy, less negative, to a lower state. These were given names, okay? When the final state is the ground state, that was referred to as the Lyman lines, okay, Lyman series, and it terminates on n equals 1, the ground state. Unfortunately, we don't see those. They're in the ultraviolet. The Balmer state, though, terminates at the n equals 2 state, and those are all indivisible, regardless of where they start from. All the ones above that terminate at the n equals 3, 4, 5, Passion Bracket Fund are the names of those. They're all in the infrared. So the one we see is the Balmer series, and that's what we studied in the lab in modern physics. I know that Campbell's class did that as well because I stole his lab handout, so you've seen this before. All right, I think I'm at the point where I got to call it a day here, so we'll quit from this. Sorry about going about 4 minutes over. Hey, any questions before we leave? All right, last chance. I'm going to set up office hours for later on today. If you're working on the hydrogen one tutorial is due today, and let's see, the tutorial on, the homework 7, which will be on the exam. It's the stuff from chapter 3 that's due Wednesday. So I'll take any questions on any of that or any other things you have, meaning of life, whatever. Last chance. All right, y'all have a great day, and we'll see you for sure on Wednesday, and the exam will be ready for you at that time. Take care now.